Okay, Samuel. So we're talking about improving our bird/airplane classifier. We had a problem with memorization, right?
Yeah, exactly. The fully connected layers were great for fitting the training data, but awful at generalizing. Too many parameters. No position independence.
So, convolution is the solution?
It's a better approach. Instead of a flat, dense connection, convolution looks at small local patches of the image.
Small patches? How does that help?
It builds in position independence. If a bird's beak is important, it'll pick that up, no matter where it is in the picture.
So, it's like it just focuses on features, not the whole image?
Precisely. It's like a sliding window, identifying key patterns, and that's a huge advantage. Imagine recognizing a cat's ears. You don't need to know exactly where they are in the picture.
Right? It generalizes better. And why is that better for, like, airplanes too?
Well, the same principle applies. The specific placement of the wings, tail, or fuselage isn't crucial. The key features will be recognized regardless of their exact location.
So, what do you gain in terms of parameters?
You drastically reduce the number of parameters needed to achieve the same level of performance or even more. That's the key. Fewer parameters means less memorization and more generalization.
That makes sense. So, this convolution approach, it's less prone to overfitting then?
Absolutely. And it's more robust to variations in the input data. Imagine if you shift the image a bit, the convolutional network will still recognize the features. Overfitting is a major headache, especially in real-world scenarios.
Great. Thanks, Samuel. So, convolutional layers really address the overfitting and position independence problems. Okay, Samuel. So you're saying convolutions are about focusing on nearby pixels? That's different from looking at everything.
Exactly.
Imagine recognizing a bird.
You don't need to know everything about the entire picture. Just the bird's shape and how its parts relate.
So, instead of a global view, we look locally?
Exactly. It's like zooming in on a specific area and finding patterns there.
And how do we do that mathematically?
Well, we use weights, and those weights only consider pixels near a central pixel.
Okay, but these weights aren't random, right?
Nope, they're learned from data, just like other weights in neural networks.
So, it's like a sliding window?
Kind of, but more like a focused lens. We slide this weighted window across the entire image.
Wait, what's the benefit?
Translation invariance. If the bird is in the upper left corner, or the lower right, you still recognize it. It doesn't matter where it is in the image.
That's awesome. How is this different from using a linear layer?
A linear layer, like NN, linear, looks at all the pixels in the image. Convolutions only care about the local neighborhood.
So, you're saying these convolutions are not looking at the entire image at once?
That's right. We only look at small regions at a time.
So, instead of massive weight matrices, these have localized, more focused weights. Makes sense.
Exactly. It's like a magnifying glass for patterns within the image, rather than just trying to see the entire picture all at once. Much more efficient. And it's critical for things like computer vision tasks, where local features are often more important than global ones.
So, Samuel, you were saying convolutions offer translation invariance. Can you unpack that?
Yeah, imagine a filter, a kernel, recognizing a cat. With a normal matrix, we'd need different weights for the cat, no matter where it appears in the image.
Right, like different equations for each location?
Exactly. Convolutions use the same filter everywhere. The same weights for that cat filter, no matter its position in the image.
How does that work?
It's like sliding the filter across the image. The filter multiplies, or performs a scalar product, with parts of the image that it overlaps. Each location in the output image is the result of this calculation.
So the same filter, and thus weights, are reused across the entire image?
That's the key. Reduces the number of parameters, which is huge for bigger images.
Why is this better than a full matrix approach?
Fewer parameters means less training data needed, and training takes less time and computing power. Much more efficient.
So, what about the local operations on neighborhoods you mentioned?
The kernel, or filter, only looks at a small area. It doesn't try to learn everything about the whole image at once. It focuses on local patterns.
So like a 3 by 3 square?
Exactly. It only looks at those 9 pixels, just a tiny region around each output point. It's very focused.
Interesting. And how does this impact the derivative of the loss?
With the same kernel, and thus weights, reused, every image location contributes to the calculation. Thus the derivative includes the entire image.
Wait, so that means this localized pattern, like our cat, has a larger impact on the output no matter its location because of the same weights influencing it in any position?
Absolutely. The weights of the convolution kernel learn to respond to patterns, and these patterns are identified regardless of their location within the image.
Are there any downsides to convolutions?
Well, it's important to choose the right size of the kernel, the filter. Too large, and you lose important detail. Too small, and you miss large patterns. You have to balance that. Also, the weights are tied, which can impact learning.
Okay, Samuel, so we're diving into convolutions now. Tell us about these 2D convolutions.
Right. Imagine you're looking at a picture. A 2D convolution is like sliding a tiny window over that image.
A window? Like a magnifying glass?
Exactly. That window is our kernel. It looks at a small region of the image and does a weighted average of the pixels within that region.
And why a weighted average?
Because different parts of the kernel have different weights. This lets the network learn which parts of the image are important.
So, this kernel slides across the whole image, right?
Yes, and that's key. It extracts features from different parts of the image. Think edges, corners, textures. The output, then, is a new image with the extracted features.
How many different kernels are we talking about?
Well, the number of output channels in the kernel defines how many different features the network can detect.
Wait, so this is how we get more complex features through the many different kernels?
Exactly. It's a powerful way to learn patterns. The more kernels, the more complex the features. That's why the output has so many channels.
And the size of the kernel? Is there any particular reason for this?
Often, kernels are square. A 3 by 3 kernel looks at a small 3 by 3 section of the image. That's really common, because it's a good balance between looking at enough context and not too much.
So, what's the role of the input channels?
That's the number of colors in the image. RGB images have 3 input channels. The kernel looks at each channel individually, but combines those channels to create features.
I see. So the kernel multiplies the input channels, performs the weighted average, and we get an output channel?
Precisely.
And what about this issue about losing pixels? Why does the output image have fewer pixels than the input?
The stride. That's the step size. The kernel stride determines how far it moves across the input image. A stride of 1 moves 1 pixel at a time. If the stride is bigger, you'll lose pixels in the output.
Okay, Samuel, so padding. Why is padding important in convolutions?
Well, Alfred, it's all about image boundaries. Imagine a 3 by 3 filter trying to process the edges of an image.
Yeah, it's got nowhere to look.
Exactly. Without padding, you lose pixels. The output image gets smaller.
So, padding adds these ghost pixels?
Artificial 0 pixels around the edges. PyTorch lets you control this.
So, we're essentially faking data?
You could say that. The convolution then has the needed neighbors to work correctly. And the neat trick? This output is now the same size as the original image.
That's amazing. How does this work practically?
Imagine processing images of handwritten digits. You want to identify the features, right? Padding keeps these critical edges in the processing.
And what if we didn't pad?
The feature detection at the image edges would be affected. If there are important details in the edge, that information would be lost.
So, padding avoids these losses.
Exactly. It separates the convolution operation from resizing the image. Makes things simpler, cleaner, and less prone to errors. And importantly, for more complex models, padding helps maintain compatible sizes for layers where we want to sum or subtract tensors.
So, there are practical benefits too? Like more efficient design.
Precisely. Think about skip connections in neural networks. They often rely on tensors of identical dimensions. Padding ensures that those inputs match up seamlessly.
So, padding isn't just about preserving the image size, but for the architecture of the whole model as well. Clever stuff.
Indeed. It's a powerful way to improve the clarity and efficiency of our convolutions.
So, we're talking about convolutional filters now. How do these filters actually learn?
Well, it's fascinating, Alfred. We can manually set weights.
Like by hand? That's interesting. How does that work, and why would we do it?
Yeah, we can manually set the weights. To understand learning, it helps to see simpler cases first. You can set the weights to something simple, for example, averaging the neighborhood.
Ah, an average filter. So, each pixel becomes the average of its surroundings. That makes intuitive sense.
Exactly. That results in a blurred image. It smooths things out, averaging the values. A good starting point.
Makes sense for blurring. But is there another use?
Sure. You can build different filters for different things. You can create filters that highlight edges in images.
Edge detection? How's that work?
There are filters that find differences in intensity. Imagine an edge between light and dark. The filter spots that difference, making the edge stand out.
Wow, like a high-pass filter, but specifically for images. So, what do these weights do in practice for these filters?
Exactly. By crafting particular sets of filter weights, you can detect specific features. Think of different filters as searching for different types of visual patterns. A lot of these filters are simple but work together in complex systems.
I see. So, manual filters are a good starting point, but how do these filters really learn in a neural network?
Excellent question. Deep learning lets the network figure out the best filters automatically. It's about optimizing the filters based on the specific task, like minimizing errors in recognizing something.
So, it's not just about finding edges or averages. It's a much more sophisticated approach, learning the best filters for a task.
Exactly. The network learns the ideal filters from data to perform the intended task most effectively, something like finding patterns.
So, Samuel, you were saying that moving to convolutional layers instead of fully connected ones gives us locality and translation invariance. But what about structures that aren't 3 or 5 pixels wide?
Exactly. That's a crucial point. We've zoomed in on small details, but how do we capture larger patterns? It's like trying to see a forest by only looking at individual trees.
Right. So, big kernels aren't the solution?
Not really. A huge kernel would just collapse back into that fully connected network, losing the valuable properties.
Interesting. So what's the trick?
We stack convolutions, but crucially, we downsample between them.
Downsample? Like shrink the image?
Precisely. Think of it like zooming out. You see more of the image, but with less detail. But this zooming out process becomes really powerful when combined with successive convolutions.
So, how does downsampling help us see larger patterns?
Well, each convolutional layer extracts features from the image. The downsampling, typically with max pooling, lets the next convolutional layer effectively operate on a wider neighborhood. This helps the network learn features that are compositions of previous ones.
So the second convolution is kind of building on the first?
Exactly. It's like an assembly line of feature extraction. The first layer might find simple edges, then the second, more complex shapes, and so on. This allows the network to recognize even very complex patterns.
Okay, average pooling and max pooling. What are those?
They are ways to reduce the size of the output. Average pooling takes the average of a group of pixels. Max pooling takes the highest value. Max pooling is more common now, even though it discards some information.
But discarding information? Isn't that a problem?
It can be, but often it helps the network focus on the most salient features. Those are the strongest, the most important ones, in the region.
And this strided convolution, what's that about?
That's another way to downsample. Instead of taking the max or average, it selectively picks pixels spaced apart, keeping more information intact. A lot of research is going into that, but max pooling is still the dominant method.
So, a crucial takeaway here is combining those layers, right?
Absolutely. This way of stacking convolutions and downsampling allows us to create a sort of hierarchical feature learning. It's a powerful tool for complex scene understanding.
In the receptive field?
The receptive field of a neuron in a later layer tells you how large a region in the original input image influences its activation. It keeps growing as you go deeper into the network thanks to the stacking process of convolutions and max pooling.
This is amazing. We've gone from small kernels to recognizing large structures. Thanks, Samuel. Okay, Samuel, so we've built a convolutional neural network. But it's got this error. Can you explain why?
Yeah, the error's pretty common. We're trying to connect the convolutional parts to the fully connected layers. The problem is the shape mismatch.
Shape mismatch? Elaborate, please.
The convolutional layers work on 2D images, reducing them through pooling to smaller representations. The fully connected layers expect a flat 1D array.
So, we need to flatten this 2D output from the convolutional layers?
Exactly. That's what we forget. The convolutional layers output a multi-channel 2D feature map, like a grid of numbers representing different features.
And how do we turn that into a 1D vector?
We use a method called reshaping. Imagine taking a grid and stretching it out into a single line. It's like a jigsaw puzzle.
Makes sense. So, adding this reshaping step to the network will fix the shape mismatch?
Precisely. The error was because we didn't tell the network to flatten the convolutional output.
This is crucial. We need to understand why this flattening is necessary.
It's essential for the fully connected layers. These layers work on a single input vector and produce a set of outputs. We need the 1D input to match the expected shape. Think of it like preparing data for a final calculation.
So, what happens if we don't reshape?
It causes a mismatch between what the network expects and what it receives. Kind of like trying to fit a square peg into a round hole. That's where the error message comes from.
Got it. So we explicitly reshape the output. But why is the size of the linear layer dependent on the max pooling output?
The size of the linear layer depends directly on the dimensions of the pooled output before flattening. That's why 8 by 8 by 8 becomes 512. The 8 comes from the channels. The linear layer's job is to process these flattened features.
That's really helpful. Thanks, Samuel. This makes it clearer now. Okay, Samuel, subclassing NN module. Why is this important? Like, why can't we just use NN? Sequential all the time.
Well, Alfred, NN. Sequential is great for simple, linear models. But when you want something more complex, like a residual connection, or maybe you need to reshape data in a custom way, you need more flexibility. Subclassing NN module gives us that.
So, you're saying it's about customization.
Exactly. We're building our own little building blocks for the network.
And how does this subclassing work?
The key is the forward function. That's where you define the actual computation. It takes the input and spits out the output. It's like the recipe for the component.
Interesting.
You define them in the __init___ function and save them to self. Then you use those modules inside your forward function. Think of it as gathering ingredients before you make the dish.
So, you initialize submodules in the constructor and then use them in the forward pass?
Right. And remember, you must call super__init__, first in the __init___ method to make the magic happen. PyTorch needs that to properly set up the parameters of the module.
Oh, that makes sense. But why super? __init__? What would happen without that?
Without super__init__, PyTorch won't know how to properly initialize the underlying module. It's part of the architecture. You are extending a class, so you need to follow the rules.
Okay, so you have these submodules. Are they independent from your custom module?
They are, but they exist within the context of the custom module, so their parameters get tracked along with your module's parameters. It's a way of organizing complex computations into logical units.
So if you need to use, say, a convolutional layer inside a custom module, you just define it within the __init__, and call it from the forward function?
Correct. It's building layers upon layers, but with custom rules.
And AutoGrad still works?
Absolutely. As long as you use standard PyTorch operations, AutoGrad takes care of the backward pass automatically. You don't have to write separate backward functions. It's automatic differentiation magic.
That's pretty cool. So, custom modules are for more complex neural networks?
Exactly. They give you granular control over the computations. You can really tailor the architecture. This is crucial for researchers and practitioners alike. But of course, NN. Sequential is perfectly sufficient for simple, well-defined steps.
Makes perfect sense. Thanks, Samuel. So, Samuel, you're saying this new net class is essentially a different way to represent the same neural network?
Yeah, exactly. Instead of using NN, sequential, we're building each layer as a separate module. This gives us more control.
More control? How so? And why is that important?
Well, we can now manipulate the output of intermediate layers. Like, we can directly reshape the output of the pooling layer before feeding it to the next part.
That's interesting. So, what's the practical benefit of reshaping?
It lets us connect different parts of the network in ways we couldn't with NN, sequential. We might need to feed different parts of the network into different places further down the line. It's like rearranging the pieces of a puzzle to fit the overall picture.
Okay, I get the reshaping idea. But what about the shrinking of the data? It seems important for classification networks.
Absolutely. Generally, in classification tasks, the data gets progressively smaller. Think of an image. We start with a huge number of pixels, and we want to compress that down to a smaller description of the image, such as its class.
So, the convolutions, pooling, and linear layers are all about shrinking this data?
Precisely. The fewer channels or pixels we have, the better we can classify. However, there's a nuance. Some architectures, like ResNet, increase the number of channels while reducing spatial resolution.
Whoa, that's counterintuitive. Why would that help?
It's a different approach to shrinking the information. It's a balance. Increasing channels can help capture more complex features, but it depends on the dataset and the depth of the network.
So, the initial layer is special. It's increasing in dimensionality?
Exactly. Think of it as building up the initial representation. It takes that raw input and creates a more robust representation, even though it's bigger than the subsequent layers. That initial step isn't just a simple downscaling.
That makes sense. So, you're saying the network's design is an iterative process where you start with a potentially large representation, and you progressively condense it. Is this a general trend in convolutional networks? Or is it dependent on factors like the dataset and network architecture?
It's a common pattern in many classification networks, yes. But the specifics, like how much and how fast the information shrinks, are very context-dependent.
Okay, Samuel, so you're saying PyTorch automatically tracks submodules?
Yeah, pretty neat, right? It's built in. If you add a module to another module as an attribute, PyTorch sees it as a submodule.
So, no extra work needed?
Exactly. Makes things
Top level? Like, not inside lists or dictionaries.
right. PyTorch won't find those nested submodules. If you need lists or dictionaries of modules, PyTorch has special tools like nend-module-list and nend-module-dict. They're designed for that precise use case.
You mentioned calling methods, like a predict method for a model?
Exactly. If you have a model that's used differently for training than for prediction, you might want a separate predict method.
And how do these predict methods relate to the forward function?
Well, they're similar to forward, but they don't have the same hooks. The JIT compiler doesn't see the module structure when using those methods. It's like a separate, independent function call for the module.
So, how does the model find the parameters of its submodules?
PyTorch's parameters method digs into all registered submodules and recursively checks their parameters. It works no matter how many levels deep submodules are nested. So a big network gets a complete view of its parts.
And the optimizer can change them?
Exactly.
Makes sense, but why register submodules with no parameters?
That's a good question. While NN, TAN and NN maxpool 2D don't have learnable parameters, registering them as submodules makes the overall model structure clear and easy for tracking in PyTorch.
So, registering them as submodules helps manage the structure. It keeps the overall structure clean. That's pretty smart, isn't it?
Totally. It's more organized and readable compared to just calling them in the forward function. But you can absolutely call them directly in forward if you really need that extra speed and don't need the extra level of organization from the submodules. It all comes down to balancing clarity and efficiency.
Thanks, Samuel. That was helpful. So, Samuel, this functional API, it's a different way of doing things, right?
Yeah, definitely. It's like having a separate function for each operation, instead of using modules with internal state.
So, no more storing parameters inside the module?
Exactly. The function just takes inputs and parameters as arguments. It's great for operations without internal state.
Like pooling and activations?
Exactly. These usually don't have parameters, so the functional way is cleaner. And it's super concise, too.
Makes sense. And you're saying sticking with modules for linear and convolutional layers is still best practice?
Yeah, absolutely. Those have parameters, and the module handles keeping track of them during training.
So, the whole training process is different now?
Not exactly. The training procedure stays the same. It's just how you construct the model's forward pass that changes.
Wait, so you're saying you can just mix and match?
Precisely. You can use functional for things without parameters, and modules for things that need those parameters. It's really about choosing the best tool for the job.
Okay, I see. What about the examples with max pooling and activation?
The code shows a forward pass using functional APIs for max pooling and TAN, a type of activation function. It's a very clean and concise method.
That's very efficient. You also pointed out a potential pitfall, right?
Yes, with reusing the same functional API for a series of stateless modules like ReLU. While it works fine in standard Python, tools designed to analyze your model might raise errors.
So, it might be best to use a new instance for each if you need several?
You're right. Using separate instances of functions for stateless modules can prevent unexpected problems.
This functional approach, is it for all situations?
It's fantastic for when you have simple stateless operations, or for building your own forward passes.
You also mentioned quantization. How does that change things?
That's an interesting point. Suddenly, those stateless functions become stateful because you need to capture quantization information. For quantized models, sticking with modules often gives better results, or might just be less error-prone, especially when you're not using just-in-time compilation.
So, it's a decision based on the situation and the type of task you're undertaking?
Precisely. Style, simplicity, and the task's complexity all play a role.
So, Samuel, we're now diving into the nitty-gritty of training our convolutional neural network. You mentioned a training loop. Explain that to me.
Yeah, the training loop is crucial. It's basically a structured way to feed our data, process it, and adjust the network's parameters to improve accuracy.
Can you break it down?
Think of it like practice. We present batches of images and their labels. The model predicts results. We calculate the difference between prediction and truth, the loss. Then, we adjust the model's internal settings, step by step, to minimize the loss. It's like fine-tuning a machine, making it more accurate with every round.
So, you're updating parameters based on the loss?
Exactly. We're using an optimizer to gradually tweak the model's parameters, reducing the error, a bit like iteratively adjusting dials on a complex machine.
And this happens in loops?
Yes, over epochs and batches.
How is accuracy tracked?
The code calculates the loss over each epoch. Then, we print that loss to see improvement over time.
So you're checking the average loss?
Exactly. It's more manageable than keeping track of all the individual losses, giving us a clear idea of how well our model is learning.
What about the code's handling of batches and epochs?
It's elegant. The data loader neatly breaks down the training data into batches, making sure the training process doesn't stall. We loop through these batches during an epoch. We calculate the loss, update weights, and iterate until the end of an epoch, where we calculate the average loss. This way, training is optimized.
Okay, so the training loop is an outer loop, epochs, nested within another loop, batches. What are the key steps?
First, we feed the input data to our model. Second, we compute the loss. Third, we reset the gradients. Fourth, we compute the gradients, backward pass. Fifth, we use the optimizer to adjust parameters. We also collect and print information throughout.
What are epochs and batches?
An epoch means the entire training dataset has been processed once. A batch is a small portion of the training dataset, processed in one step. So the entire dataset passes through the loop in a series of steps, epochs, each step containing several batches.
So you're essentially doing gradient descent in batches?
That's right. It's a smart way to train our model efficiently. It keeps things manageable by not dealing with massive datasets at once.
And what about this SGD optimizer? What's that all about?
Stochastic gradient descent, SGD. It's a common optimization algorithm in deep learning. It updates parameters by calculating gradients on small samples, not the entire dataset. It's faster and more practical with large datasets.
Great overview, Samuel. So, we're aiming to train our network, minimize the training loss, and iterate through epochs and batches, updating the model step by step using an optimizer like SGD.
Precisely. Now, the choice of the right optimizer and parameters is crucial for the effectiveness and speed of the training, which we'll explore later. Good question.
So, we're looking at accuracy now, right? How is this accuracy calculation different from just looking at the loss?
Yeah, the loss function tells us how wrong our model is, but it doesn't directly tell us how often it gets the right answer.
Makes sense. So, you're calculating accuracy on both training and validation sets?
Precisely. We want to see how well the model performs on new, unseen data. That's what validation is for.
And what's the code snippet doing? Break it down for me.
Well, it creates data loaders for the training and validation sets. Then, a validation function iterates through these sets. Crucially, it doesn't need gradients during this stage.
Why not gradients?
Because we're not updating the model's parameters, we're just testing its predictions. It's like taking a quiz. You don't get to adjust the questions after each answer.
So, it makes predictions on the input images.
Correct. It then finds the predicted class with highest probability for each image.
And how does it calculate the accuracy?
It compares these predicted classes to the actual labels. It counts the correct matches, divides by the total number of images, and that's the accuracy.
So, this function, takes the model and the two data loaders. What's the output of this function?
The function prints the accuracy for both the training and validation sets.
So, the output of this code, 0.93 for training and 0.89 for validation. That's a significant improvement, right?
Definitely. Compared to the previous fully connected model, the improvement is really quite impressive. This shows a substantial reduction in errors and fewer parameters. That's crucial for generalization.
So, the model is performing better on new data than the fully connected model, thanks to this locality and translation invariance idea?
Exactly. It's more robust. The model's learning meaningful features across different parts of the input image, not just very local things. That's a big win.
That is really important, I think.
Yeah.
So, we've trained our model. Now saving it, right? Tell me about this.
Yeah, saving's crucial. We want to keep our hard work. This code saves the model's learned weights and biases.
Just the amounts? Not the instructions?
Precisely. The actual structure of the model, the layers, the connections, remains the same. We save only the learned values. This lets us load it later.
Why not save the whole thing?
Well, it's often really large, especially with complex models. Saving everything is huge, and takes a lot of time and space.
So, we save just to learn stuff, and then what? How do we use it?
We load it back into a fresh copy of the same model class. It's like having a blank recipe book. We then copy the ingredient amounts into that book.
You have to make sure the book is exactly the same?
Exactly. Otherwise, the amounts won't fit. We wouldn't want to mix up our cookie recipe with a cake recipe, right?
Makes sense. So, loading is like filling in the blanks of a pre-designed form.
Exactly. The critical part is that the model architecture must remain identical when loading. If you change the model's recipe in any way, add an ingredient or change the instructions, the saved weights might not fit.
Gotcha. So, we save the weights and biases. Then what? Load them into a new model of the same type, and we're good to go.
Precisely. That loaded model is ready for new data. Our friend who wants to use the model will need the model class. They don't need the entire training process. Just the learned values.
So, it's like having a pre-trained expert chef. You've learned all the complexities, so you don't have to do the whole training again.
Absolutely.
Okay, Samuel, we're talking GPU training now. So, why is moving things to the GPU important?
Well, Alfred, training on a GPU is significantly faster for deep learning models. It's like having a superpowered processor for your computations. Think of it like having a bunch of tiny calculators working in parallel.
Okay, but how does the code handle this?
We use a.to method. It's a really neat function. It moves your data and model parameters to the GPU if one's available, or to the CPU otherwise.
So, is that function used for different things? Like for tensors or modules?
Exactly. You use .to on tensors to move them, and on the module itself, and it moves all of its parameters to the GPU, which is super convenient.
So, what's the difference?
Tensor to is out of place. It creates a new tensor on the desired device. Module.to modifies the module in place, which is more efficient.
I see. So it's a matter of efficiency?
Yes, for performance reasons, it's ideal to create the optimizer after you've moved your parameters.
Gotcha. And how do you actually set this up? The code example shows using torch.device. Why that?
That's just a clever way to dynamically choose the device, whether your computer has a GPU or not. It sets up the device to be used.
That makes sense. So, the code snippet shows how to modify training and validation loops, right?
Yes, the only difference in the training loop is the addition of ims equals ims to device and labels equals labels to device. This ensures that data is on the correct device for calculations.
So, if you don't move the data to the GPU, will your model not work?
Absolutely. PyTorch won't mix GPU and CPU inputs in its calculations. Errors will happen.
And what about saving and loading models on different devices?
You have a couple of choices there. You can move the model to the CPU before saving it, or instruct PyTorch to ignore the original device and load to the specified one during loading with map_location. The map_location approach is often preferred because it's more concise.
Interesting. So, in practice, what are the pros of using GPUs?
Larger models benefit a lot more from GPUs, but even small ones see a performance boost, as illustrated in the example code. The increased speed is a big win.
So, pin memory. Is it essential for improving training speed?
There's a pin_memory option in the data loader to make transfers faster. However, the actual gains vary, so it's not a necessity in all cases.
So, we've trained simple models, now what? More complex problems, right? Like ImageNet?
Yeah, ImageNet's a whole different ballgame. Those images are huge, lots of details. One thing matters a lot in complex problems. Multiple clues are usually involved.
Multiple clues? Like maybe a car has wheels and 4 doors? Makes sense.
Exactly. You can't just look at one thing. It's often a hierarchy, different levels of information. Think of recognizing a cat. You might first notice pointy ears, then a tail, then the whole shape.
So, PyTorch has got tools for these complex scenarios?
Absolutely. PyTorch has a huge library, tons of modules and loss functions. You can build almost anything with the right combination.
Like, say, a problem involving not just pictures but also text or numbers.
Yup. One powerful idea: neural networks can handle many different data types. Table data, sequences, text, all possible. The architecture's key: connecting those layers and modules properly.
And what about the loss function?
You choose the loss function to match your task. Different loss functions for different jobs. It's crucial how you measure the difference between your prediction and the actual result.
Is there a drawback to using pre-built modules? What if you need something very unique?
You can combine modules to build your architecture. That's the power of PyTorch. It's flexible, allowing you to tailor your network to specific needs. And honestly, many researchers have tried these ideas.
So, building a cutting-edge network from scratch isn't always necessary?
Not at all. There's so much available. PyTorch Hub, Torch Vision, a treasure trove of existing models.
Makes sense. This makes building new networks easier?
Definitely. You can build on existing work, learning from others' successes. More time to actually solve the problem, instead of reinventing the wheel.
Interesting. So, what if you stumble upon a new paper with a fantastically innovative network architecture?
You can likely implement it with PyTorch. Understanding the concepts makes it a lot easier.
Great. So, you're saying PyTorch is ready for any challenge now, regardless of the data?
Well, not any, but most. Its flexibility, tools, and community are key. It's a strong platform. Makes it practical, almost.
Okay, Samuel, we're talking about expanding a neural network. You mentioned width. Tell us more about how increasing the width affects the model's capacity.
Yeah, increasing the width, meaning the number of neurons per layer, significantly impacts a model's capacity. Think of it like adding more lanes to a highway.
More lanes, more traffic, right?
Exactly. More lanes, more potential for parallel processing, and more importantly, more parameters.
So, more parameters mean more what?
More flexibility. The model can potentially learn more complex patterns from the data. It's like having more tools in a toolbox.
But doesn't that also increase the risk of overfitting?
Absolutely. With more parameters, the model has more potential to memorize the training data, even the noise in it, rather than learning the underlying patterns. It's like memorizing every single detail of a textbook instead of understanding the concepts. Overfitting leads to poor generalization on unseen data.
So, how does this new width-parameterized model help us to avoid overfitting?
Well, this model's example demonstrates a way to adjust model width using parameters. We now have parameters for adjusting width, making it adaptable for different problems.
So, what's the trade-off?
The trade-off is between model complexity and its ability to generalize. Wider networks might perform well on the training data, but struggle on new data. Finding the right balance is crucial.
And you mentioned augmenting the data. Can you elaborate on that?
Data augmentation is a technique to artificially increase the size of our dataset. We can modify existing data through transformations like rotations, flips, or adding noise, creating synthetic data samples. This helps the model to learn more robust representations of the data, reducing overfitting.
Clever. What about that number? 38,386. What does that represent?
That's the total number of parameters in the model. It's a measure of the model's capacity. The more parameters, the more complex the model can potentially learn.
Got it. So, more capacity, but also more potential for overfitting. You're saying we should try to increase the sample size if we can, but augmentation is useful in the absence of that?
Exactly. Increasing the sample size is generally the best approach to combat overfitting. But augmentation is a great stopgap measure if you can't get more data.
Okay, Samuel, so we've talked about optimization. Now let's dive into generalization. How do we ensure our models don't just memorize the training data?
Right, Alfred. Generalization is crucial. Models need to perform well on unseen data. Regularization helps with this.
Regularization? Can you explain that?
Sure. Imagine training a model to recognize cats in pictures. If it only sees pictures of ginger cats, it might incorrectly learn that all cats are ginger. That's overfitting. Regularization techniques prevent this.
How does it do that?
It adds a penalty to the loss function. Think of it like a fine. Big weights increase the risk of overfitting. The penalty discourages overly large weights.
So, a penalty for complexity?
Precisely. L2 and L1 regularization are common methods. L2 is the sum of squares of all weights, and L1 is the sum of absolute values. They're both scaled by a small factor, a hyperparameter we tune.
A hyperparameter? I'm not familiar with that term. Can you clarify?
A hyperparameter is a setting you adjust before training, like the learning rate. It affects how the model learns. It's a way to control the model's behavior during training. And that hyperparameter influences the penalty.
Okay, so it's basically tweaking a control to reduce complexity. But why the squares or absolute values? Does that have a special impact?
Well, the squares or absolute values in L2 and L1 help make the loss function smoother. A smoother loss function is generally easier for optimization algorithms to deal with. You're less likely to get stuck in local minima.
So, L2 is weight decay?
Yes. Weight decay. During optimization, the negative gradient of the L2 regularization term decreases each weight proportionally to its value. That's why it's called weight decay. You're reducing the size of the weights. PyTorch's SGD optimizer even has a weight_decay parameter to directly implement L2.
That's intriguing. So, it's like systematically shrinking the weights during training.
Exactly. Less complex models generalize better. And L1 regularization, with its absolute values, is even more aggressive. It shrinks weights more drastically, promoting sparsity.
So, how about dropout?
Dropout is another powerful regularization technique. It randomly zeroes out activations of neurons.
Zeroes out activations? Can you explain?
At each training step, it randomly deactivates some neurons, forcing the network to learn more robust features. Think of it as training multiple slightly different networks simultaneously. The model learns to adapt to a lack of specific neurons. This means it's less reliant on a single combination.
It's like simulating different data conditions?
Yes, it's a form of data augmentation, but it operates at the neuron level. And to be clear, in evaluation mode, dropout is turned off.
Great. That helps. And batch normalization?
Batch normalization rescales activation inputs. It makes the training process more stable by avoiding saturated activation functions. It's another regularization technique that improves training speed and reduces dependence on initialization.
So, it effectively controls the input to activation functions?
Yes. It normalizes data during the mini-batch update. During evaluation, it uses pre-calculated values rather than mini-batch ones, maintaining consistency.
You know, Samuel, this sounds like a fascinating field.
It is. And these techniques, when used together, can significantly boost a model's ability to generalize and avoid overfitting.
Okay, Samuel, you were talking about depth in neural networks. So, deeper networks are always better, right?
Well, it gets complicated. Increasing depth can improve a model's ability to learn complex patterns, but it's not a simple case of more equals better.
Can you give me an example?
Sure. Imagine identifying objects in a photo. A simpler network might just spot a shape, but a deeper one could pinpoint the person, their face, even their mouth. That's because deeper networks can process hierarchical information, like understanding context.
So, depth is about sequential operations?
Exactly. It's like a series of instructions. Find the boundary, then the head, then the mouth. The more steps, the more intricate the task. But there's a catch.
What's the catch?
Training deeper networks is harder. Imagine a really long chain of calculations. Each step involves multiplying numbers. Small numbers multiplied repeatedly get really tiny, and large ones can dominate, effectively making the early layers' influence vanish.
So, vanishing gradients?
Precisely. The contribution of the early layers' parameters to the overall learning process fades away.
And that's why training really deep models is a problem?
That's the problem, and it was a major hurdle until ResNets came along. They introduced a clever trick: skip connections.
Skip connections? Can you explain?
Think of it like a shortcut. Instead of just letting the data flow through each layer, skip connections add the output of an earlier layer directly to a later one. This creates a direct path to the final output, essentially bypassing some of those multiplying steps.
Why does that help with vanishing gradients?
That direct connection ensures parameters in deeper layers have a more significant influence on the final result. So their contribution in the learning process is not diluted by a massive chain of operations.
So, it makes learning smoother?
Yes. That direct path also produces a smoother loss landscape. It's easier to find good parameter values. It's like a flatter terrain versus a steep, winding path.
That makes sense. But this is not something entirely new, right?
You're right. Skip connections weren't invented with ResNets. Other architectures, like highway networks, used them. But ResNets popularized the approach, allowing for networks with hundreds of layers.
So, what's the significance for larger datasets?
This is crucial, especially for complex images like ImageNet. It lets us build much deeper networks that are capable of handling this intricate information.
And how do we implement these deeper networks in PyTorch?
We use building blocks, like a convolutional layer, a ReLU activation, and a skip connection. We create a module for one block and then assemble many of these blocks together to create the entire network.
You are using a for loop to implement this, right?
Exactly, and PyTorch's NN sequential module makes that process incredibly efficient. By sequencing these blocks, it ensures the outputs of one block feed directly into the next.
So we've established this process. However, what about weight initialization?
Important. Default PyTorch initializations aren't always optimal. You might have to adjust the variance of weights, batch norm outputs, to ensure good convergence.
Are there any common pitfalls or misconceptions about using depth in neural networks?
People often assume more depth automatically means better performance. But it's about effective depth. We need the right architecture to utilize that depth.
Great explanation. Thanks, Samuel. Okay, Samuel, you've looked at different network designs. What's the takeaway here? Are we seeing big differences?
Not really, Alfred. The designs are performing similarly.
So, no huge wins from these changes?
Not in this particular setup. But important considerations are revealed.
Like what?
The graphic shows, well, surprisingly similar results.
How interesting. So what's driving this similarity?
The experiment's pretty simple. Things like learning rates and training epochs could easily change things, and those are variables we definitely tweak in a real-world project.
So, these initial results are just a starting point?
Absolutely. You need to experiment with different hyperparameters to optimize the model.
Right. And what about these weight decay and dropout techniques? You mentioned them earlier.
They're actually quite important, especially compared to batch norm. They're more robust statistically. Remember, batch norm is a convergence tool, not a true regularization.
So, dropout and weight decay have less variance in results?
Exactly. The gap between validation and training accuracy is tighter with them. Batch norm lets the network get to high training accuracy, but the validation results often diverge.
So, batch norm might be less useful if the goal is to avoid overfitting?
Precisely. Dropout and weight decay give us more confidence in generalization to new data. It's about how well the model learns patterns in the training set while also being able to recognize new examples.
Interesting. Thanks, Samuel. I think we got a solid grasp of these design choices now. So, Samuel, you're saying deep learning architectures change fast?
Yeah, they evolve super quickly.
So, what's the takeaway for a practitioner? Like, what do we do with constantly changing models?
We need to focus on understanding the math behind the papers.
Okay, but why? Why not just use the latest, greatest code?
Because the latest code is, well, it often comes and goes. The core ideas, the math, that's what stays useful. Learning how to translate math to code is super important, like a key.
So, you're saying we should ditch the latest code and focus on the principles?
Not ditch it completely. You should absolutely learn how those amazing models are implemented. But the foundation, the underlying mathematical principles, are the real gold.
That makes sense. So, you're emphasizing fundamental understanding.
Absolutely. And practicing translating those concepts into PyTorch or any framework.
That's a valuable skill. How does that link back to, say, a reinforcement learning model?
You can adapt those fundamental skills to learning all sorts of models, including reinforcement learning ones. The principles are transferable.
Right. We've learned a lot about building models. It's about translating ideas to code.
Exactly. And keep practicing it.
So, what about beginners? How can they get started with this idea?
They should focus on the fundamentals. It's about translating algorithms, the step-by-step process of a model, into code. A good base is crucial.
Okay, Samuel, so we've trained this image recognition model, but it's got limitations, right?
Exactly. We've created something useful, but we haven't solved everything.
Like what? What are the key unknowns?
Well, one big issue is object detection. Our model can't find a bird within a larger image. It just tells us if a whole image is a bird. We need bounding boxes.
Bounding boxes? Like drawing boxes around the object?
Yeah, it's tricky. You know, think about a picture of a park. There's a bird, there's a person, there's a tree. Our model can say, bird or not bird. But it doesn't know where the bird is.
So it can't pinpoint the bird?
Correct. That's a different task than what we've built so far. A completely different model would be needed for that.
Gotcha. Anything else?
And then there's the problem of overgeneralization.
Overgeneralization? What's that?
Our model's really good at recognizing what it learned to recognize. Birds, planes. But what if something similar shows up, like a cat? Our model might think it's a bird, maybe even with high confidence. It's mistaking something very unlike what it's trained on for a bird. This is a common issue, especially when real-world images aren't exactly like the training data.
So it's kind of like recognizing a blurry photo of a bird and being 99% sure it's a bird when it's actually something else?
Exactly.
Okay, so we've hit on some real-world challenges. Are those solvable?
Absolutely. But, these problems require different approaches. We need models for object detection, and we need to be more careful about how we apply our models in the real world.
Right. So this chapter highlights limitations to the current model and why we need to move forward.
Exactly. This leads nicely into part 2. We're stepping up from these smaller image problems to tackling a much larger, much more significant, real-world problem like lung cancer detection. It's the next logical step for this technology.
Lung cancer. That's a big one. How does that even work in terms of images?
Well, we can use images to analyze the lungs, looking for abnormalities, patterns indicative of cancer. It will use a lot of the things we've learned, including convolutional neural networks, with complex image processing and analysis to look for those signatures.